Hello everyone, my name is Mabasha Shaik. Now I am going to explain time aware approximate nearest neighbor search for dynamic document retrieval. Basically, the information gets changes faster than ever. News articles is get updated every minute, and research papers get revised, and social media stream never stop evolving. Yet, most of the information retrieval systems from search engine to chatbot still assume that one thing that data is static. That assumption doesn't hold anymore. When we search something like AI breakthroughs in healthcare, the relevant document today might not be same once from the 6 months ago. We need a system that not only finds the what is relevant but also what relevant right now. That is the motivation behind my project. And basically in traditional search systems and even in modern ANN algorithms, they convert the high dimensional yeah, embeddings and find the nearest neighbors for a given query. This works great, but however, data is um, doesn't add it to database. When coming to the dynamic real world scenarios like news articles, research papers are revisited. Um, old one expires or became irrelevant if documents keep arriving, and rebuilding indexes every time it will take computationally expensive. And even we ignore this and continue using ANN, then it will give the outdated information results, which is unacceptable for time sensitive domains like news searches and researchers. So the idea for this to avoid this is time adding time to the similarity search, uh, like a timestamp approximate nearest neighbor search. In this, every document isn't just represented by its embedding vector but also time interval. So when user searches for something, the query includes not only just text but also timestamp, and it finds the most similar documents that are valid at a particular timestamp. And behind the algorithm, it has two data structures. One is a timestamp graph, another is a historic near neighbor tree. Both combined together form the foundation of the time where ANN algorithm. Timestamp graph in it, like a graph, each node represents the document embeddings, and each edge is a semantically similar nodes. Each edge connects the semantically similar nodes. In timestamp graph, the edge carries the time information, showing when two documents are simultaneously valid. And in node, it contains both the primary neighbors and backup neighbors. Primary neighbors means currently active links, and backup neighbor means links that became active later or serves as a replacement when others expire. And here it will handles the dynamic updates like insertion and expiration. Insertion means adding a new document embeddings into graph with a given validity period. Expiration means it removes or deactivated outdated documents once their time window ends. And for both operations are tracked in the historic neighbor tree, which records each neighbor was active. Coming to historic neighbor tree, over a time each node neighbor list changes, which make a huge if tracked separately for every timestamp. So it became very complex and take more time and space complexity. So to compress this efficiently, we use the historic neighbor tree. So it stores the validity intervals for each neighbor in a hierarchical tree. Each tree node represents a time interval. So a neighbor that stays valid across multiple timestamps is stored only once in the highest level node that covers the whole period. So here that memory reduces from order of m square n to mn, order of mn. And next, and here query processing, the time where ANN search. Previously we have discussed data structures what we have used like timestamp graph and HNT, historic neighbor tree, for storing and maintaining the tree, all queries and timestamps. Now actual main process is doing in this using the timeware ANN search. When a query arrives with a timestamp starting from the random entry point in the timestamp, and it uses the greedy traversal like HNSW, moving towards the most similar to the query vector. At each step, retrieves the neighbor valid timestamp using the historic neighbor tree. Like if we are traversing any tree, it will first it will goes for left and then it child node, then its child node, like that it will traverse continue until no better nodes are found, and finally it returns the top case semantically similar and time valid documents. This approach gives a perfect balance of speed, memory efficiency, and temporal accuracy. And this is the algorithm. First it select any random entry node in TG and initialize the priority queue while the search is not found until it will do like it will not converged, means it will it will not find related to that timestamp. It will checks that like first if it goes to another neighbor, it will checks like that, and then it will find the similarity search. If not visited, then add it to priority queue. And from the find from the priority queue, it finds the highest similarity and returns the top most similar and time valid nodes. Here is the time complexities for this. We have three approaches here. Navy time aware nearest neighbor search. It is the slowest, and space complexity is also order of m square n. And coming to time aware nearest neighbor search using the timestamp graph, it will take order of log square n, and space complexity is m square n. And here our model is like tan plus hnt, which is taken the time complexity of order of log square n, and space complexity is order of mn. It is the most efficient and compressed time storage. It is an example, like first create a query embedding. The system converts the query into 768 dimensional embedding using a model like batch, and traverse the timestamp graphs. Then it will compute the similarities, um, compute the cosine similarities. Like query has their TF IDF values, and for document and for second document and third document, and it has their timestamps also. And finally it finds the cosine similarities of three documents. Then it will apply the time filters. Here you can see that D1 is exclude even though it has the highest cosine score, and D2 is eligible, and D3 is not excluded. Only D2 is remain valid because our query um, is between the from June to December, so it is eligible. Now I will show the execution of this code. Here you can see that firstly we have the import libraries which are useful, and then we have gone through timestamp graph class. Like here firstly we find the embeddings, and then we will then we will which the init method initialize the empty directory called graph, where each node represents a document and stores its embeddings nearest neighboring nodes and valid period. The add node function is used to insert a new document into a graph, and then here active node function retrieve all nodes that are valid at a given timestamp, ensuring only consider documents that are still relevant at the time. And finally, expired nodes removes all nodes whose validity period has ended before timestamp. And coming to the third cell, here we use the insertion, TG insertion and expiration. In some, the insert point function is used whenever a new document enters the system. It first calls the add node tg dot add node, and then to add the new node with the embeddings and validity time range. Then it calculates the cosine similarity and all existing nodes to find the how semantically close they are. These similarities codes are stored as the candidate pairs and stored in the descending order. As the new node is connected to its top m nearest neighbors using the bidirectional edges, this ensures that documents are linked to the most relevant ones in the graph. And the expire point is the responsible for to remove the documents, and and we will find the cosine similarity of that. Then um, historic neighbor tree, it will here um, here first the update method dynamically records these relationships as the time progress. When it called, it first checks if node is already existed in the history. If not, it initializes an empty list for it. Then it retrieves the current list ongoing neighbors, enters it add any neighbors that were not previously connected, marking them as a starting at the current timestamp with ongoing status. Then get valid neighbors function retrieves the all neighbors of a node that are still valid at a specific timestamp. It checks if a neighbor validity includes the interval, considering the ongoing relationship as still active. Then here in 60 cell we have taken the data set, and then we have gone through the dynamic simulation and visualization of the timestamp graph, and also visualization of the timestamp this historic neighbor tree for D2. Uh, this is about my project, and I will give conclusion for this is basically uh, for normal ANN it will take only historical data and historical data for similarity search, and for uh, searching the dynamic document retrieval it will must knows that documents are arriving every minute, every second, like news articles are added every news second, and also mm, also these research papers are revised, and for this search, for the similarity search, it will timestamp is very important and crucial for that similarity search. Otherwise, we can't search that it cannot gives the relevant documents. So in rapidly changing world, time is very important, has relevance. So the time where approximate nearest neighbor algorithm bridges this gap, combining the semantic power of ANN with the intelligence of a temporal filter by integrating the timestamp graph and historic neighbor. It delivers the lightning fast queries, dynamic adaptability, and time accurate retrievals. Thank you.